Hi everyone, Mr. Lee here. In this video, we're going to go over two types of collisions. The first type of collision is what we call the inelastic collision, and the second type of collision is what we call the elastic collision. We're going to go over the definitions of both and how to set up your formulas so that you can solve any problem. Let's get started. So the first type of collision that we're going to go over is called the inelastic collision. Now, if we're going to do a quick little English lesson here, the prefix in or in, that means not. So what this translates to is not elastic or non-elastic. And that's just a really fancy way of saying that the objects are sticky or sticking together. Okay? So here's a just a quick little scenario that we can come up with. Let's say we have a blue like clay, right? We have this clay sphere, and this clay sphere, it is running into, let's say, a red sphere. Okay, so we have a blue sphere and we have a red sphere. Let's say the blue sphere and the red sphere, they're going to run into each other. So we have the red sphere with the velocity to the left, a blue sphere with the velocity to the right. Okay, so here is our scenario. What I like to do is whenever there is an interaction or a collision that happens, I like to represent that with two parallel dash lines like that. And in my brain, I like to think of that as a after the collision, or in terms of what you'll see in a little bit, this is like an equal sign. Okay. All right. So after the two collide, let's say they stick together, they kind of stick together like so, and we get a combination of a blue sphere and a red sphere, kind of like that. Okay, all right, and let's say after they collide, they have a overall velocity to the left. Okay, so v final, like so. All right, so if this is our scenario, this is a inelastic scenario because the two objects, they combined into one. And if we were to come up with a equation, we got to use this idea called the conservation of momentum. So conservation of momentum says that the momentum of the system before is equal to the momentum of the system after. So we would write it something like this. Momentum before is equal to the momentum after. And if you remember from the energy unit, the momentum before and the momentum after, or the energy before and the energy after, we're looking at the system as a whole. So in this case, the system would be the blue sphere and the red sphere. So I would write it something like this. We will say that the momentum of the initial blue sphere plus the momentum of the red sphere. Okay, so you see how these two parallel lines, that's like representing my equal sign. So the two momentums before is equal to, now look what I do here. Okay, I'm going to combine the two momentums, so we'll just say the momentum final, but you'll see what I mean by that in the next line here. We know that the equation for momentum is the mass, so mass of the blue sphere times the velocity of the blue sphere, okay, plus the mass of the red sphere plus the velocity of the red sphere, initial, these are all initials, is equal to, so after they combined, we can say that they combine by using parentheses. We can say that the mass of the blue sphere plus the mass of the red sphere. So visually you can see that because we have the parentheses, we can see that the two masses have stuck together, right? They're encompassed by this parentheses. And that holds true when we are doing this mathematically. And we can say that they have a final velocity like so. So this right here, this would become our equation. And this equation will help us determine whatever we need to determine, such as like the final velocity. What is the final velocity? Okay. Now, a couple of things to keep in mind. We did this scenario without any numbers. So the first thing is that this is all in one dimension. Okay. So everything here is moving along the x-axis, and we can have this moving along the y-axis. But right now, we're just worried about one dimension. We're not worried about x and y. And also, you need to keep in mind that we didn't do any numbers here. So anything that is moving to the left or downwards, okay, we always say that those velocity vectors will be negative. So velocity will be negative. Now that's important to keep in mind, especially when we are solving these numerically. All right, so that was a 2-object system. Now I just want to show you what would happen if we were to change this to, let's say, a 3-object system. So let's say, I'm not going to do the colors this time. We have object 1, and object 1 is moving to the right, and we have object 2. Object 2 is also moving to the right, and then we have this massive object 3. Object 3 is moving to the left. Okay, so here we have a 3-object system, and let's say they all collide, okay, and they create this giant blob, right? This is objects 1, 2, and 3, and let's say it's moving to the right. Okay, so if this were our equation, and we were to come up with the conservation of momentum equation, we would always start off with momentum initial is equal to momentum final. Okay, and then because this initial momentum is describing the system as a whole, we have to have momentum 1 plus momentum 2 plus momentum 3 is equal to the final momentum overall. From there, we can break it down even more. We can say mass 1 v1 initial plus mass 2 v2 initial plus mass 3 v3 initial is all equal to, now see what I do here, I'm using parentheses trick, is equal to m1 plus m2 plus m3, because they all combine and they all share a velocity. Okay, so what that means is like this section of ball 1 and this section of ball 2 and this section of ball 3, because they combined into like this one giant ball, it's all moving with the same velocity. Okay, and so the strategy will always be the same, right? Look at the system. I highly encourage that you always draw out the system because it really helps, especially when you want to see like how to create the conservation of energy formula. Next, see what's in the system. So here we have a 3-object system. So also that really helps when you want to create your formula, the drawing part that is, and then from there expand that to your equation and see what you are looking to find. And once again, in this formula here, because we have object 3 moving to the left, that will have a negative velocity, but that's just a quick little reminder. All right, so this is what we call an inelastic system. And a couple of things to note for an inelastic system, the energy for an inelastic system, energy is not conserved. Okay, so this is one of those questions that you'll come across, especially when it comes to multiple choice. Energy is not conserved, and we can determine this mathematically. For example, if we were to be given numbers for this scenario above, we could find that the kinetic energy of the blue ball and the red ball before will not equal to the kinetic energy of the blue ball and the red ball after. And you know what, let's try that. So we can say that the kinetic energy of the blue ball plus the kinetic energy of the red ball does not equal to the kinetic energy of the blue and the red ball. And we know that because kinetic energy is 1/2 mv squared plus 1/2 mv squared, right? And we have the mass of the blue, mass of the red, velocity of the blue, velocity of the red. The two will not equal to each other because the kinetic energy formula will be 1/2 mv plus mr v squared. Okay, so if we take a look at this here, this final velocity right there, it's not going to be big enough to make this equation come true. So mathematically here, I'm going to highlight this, but I'm going to highlight the things that we can take out. So we have 1/2 that we can take out, and that's about it. So we have 1/2 times mb vb squared plus mr vr squared. Okay, and this visually doesn't even come close to what this looks like, right? So even mathematically, if we were to do numbers and we were to plug in the numbers there, we will see that the energy is not conserved. Now, why is that? Why is that? So yes, the math turns out the energy is not conserved, but conceptually, we should be able to explain why. And the reason why is that when collisions happen, okay, when collisions happen, there's some form of deformities. Deformities occur, right? So deformities occur, and deformity just simply means that the object like kind of like bends in a little bit or like mutates a little bit, and so the object doesn't retain its shape. Okay, and when collisions happen, energy is lost. Usually, energy is lost usually in the form of heat, and this is something that we know because if you were to, you could try this with me, but if you were to get your hands and you were to clap your hands together, right? The more that you clap your hands, the more heat is generated. And we always say that heat is unusable energy, and it is energy that is lost. So energy is not conserved. All right. The next type of collision that we're going to look at is what we call the perfectly elastic collision. Okay. So perfectly elastic collision. Now, these are what we usually use to describe things like a very theoretical situation. And I think in the real world, this is like what happens with atoms, right? When atoms collide, it's usually a perfectly elastic collision. But this is a very theoretical idea. But the main idea here is that energy is conserved. Okay, energy is conserved in a perfectly elastic collision. Now, in the real world, when objects do hit each other, energy is lost. So in the real world, we do not have perfectly elastic collisions because energy is lost. But for a lot of the physics examples that we use, we usually consider it to be a perfectly elastic collision. And it just makes everything so much more cleaner. Okay, so what does this look like? Well, elastic means that it is bouncy or it bounces off. And we know that because inelastic, remember, in is a prefix for not, so not elastic. So elastic is when things are bouncy. So if we were to come up with a scenario, let's say we have a blue ball, right? And then this blue ball, there's a red ball here, and the two blue and the red balls, they will be running into each other. Okay, and after they run into each other, they bounce. All right, so they bounce off. For the sake of showing the different kinds of collisions, I'll just say that the blue ball, it bounces off, and the red ball bounces off, but they bounce off in a way so that the blue ball is still moving forward and the red ball has changed its course. So this is to the right, this is to the left, and after the collision, right and right. And usually this happens when one of the balls has more momentum or more inertia, and it can change the course of the other ball. So imagine like if, I don't know, like an 8-year-old, right? So we have a tiny little 8-year-old, okay, and this 8-year-old for whatever reason is fighting against a WWE superstar, right? All right, so I'm a WWE superstar, I'm super buff. Yeah, those are, I don't know what those are. Those are the hands, those are the fists, right? And that's like the wrist guards to protect the muscles, right? And then they have the championship belt, right? Because I'm a WWE superstar. Wow. And they have shoes on. Okay. And so in this in this scenario here, if that, I don't know, how old are they? 7-year-old. The 7-year-old were to run into this WWE superstar, right? The WWE superstar and all their glory will continue running past the 7-year-old. Poor 7-year-old will be just like obliterated. All right. So just letting you know that it doesn't always have to come into a situation where the two rebound off of each other. All right. So in order to come up with the equation here, the process is the same. We say that the conservation momentum states that the momentum initial is equal to the momentum final. And we just take a look at the system as a whole. We say initially we have a momentum of the blue plus the momentum of the red. And after, because they did not combine, we can say that the momentum of the blue final plus the momentum of the blue, oh, that should be red, excuse me, momentum of the red final, they have to equal to each other, right? So we'll put a little O there for initial. Okay, and so from here we can break down the equation even more. We know that the momentum equation is mass of the blue plus the velocity of the blue initial plus the mass of the red velocity of the red initial is equal to the mass of the blue, velocity of the blue final, plus the mass of the red plus the velocity of the red final. Okay, and this is what it would look like for a two-object system. And same as always, be careful for objects moving left or down, because whenever objects moving are left or down, we say that the velocity is negative. Okay, all right, and it doesn't get any more complicated than this. I always draw this system and this scenario, and so should you. And from there, you can easily determine how to set up the equation. And based on the problem, you're probably going to be given any missing variable, and all you got to do is figure out what that missing variable is. Okay. All right. So this is for perfectly elastic collision. Just as a highlight one more time, energy is conserved for a perfectly elastic collision. Usually, energy is lost in the form of heat, either that or deformities of the object. We also talked about how the inelastic collisions, they do not conserve energy at all, and we discussed how we can draw the system and the scenarios to come up with the conservation of momentum equation to solve for the missing ideas here. All right, cool. Well, that's it. Good luck, and next time we'll take a look into how the forces or outside forces can impact the momentum of a system. Bye-bye.